In this lecture, we're going to review the concepts related to frequency domain. This lecture also has a few exercises that you can attempt on your own. For more practice exercises, refer to lecture 15. Here we are going to cover everything that was introduced in the frequency domain, and the first thing to look at when you deal with functions in the frequency domain is, of course, the phase and magnitude of a transfer function. This is the key concept for everything that follows. Thus, it is extremely important that you are able to calculate the phase and magnitude of the transfer function easily. For a generic transfer function g of s, this function can be expressed as a ratio of polynomials for zeros and for poles, and everything multiplied by again k. In this particular example, the zeros are noted as z and poles as p. A generic transfer function can then be expressed as the product of different zeros, where z can be a real or an imaginary number, divided by the product of all poles. In the same way, p can be a real or an imaginary number. Everything here is multiplied by a constant gain k. Remember that now we are evaluating the phase of the transfer function and the magnitude of the transfer function in a steady state in the frequency domain. This means that the input to the system is a sinusoidal waveform of frequency omega. This means that this function can be now written as a function of j omega, where s is j omega, omega is the frequency, the input, and the term sigma that belongs to the definition of the variable s is simply neglected here because you're dealing with a steady state. So all transients that are generated by having an exponential component in the system are neglected. To evaluate the phase of the transfer function, we can take a similar approach. This is well described in the Cauchy's argument principle, defined in an earlier lecture. The phase of the transfer function is simply the phase of all zeros, or each individual zeros added together, minus the phase of each individual pole added together. And of course, plus the phase of a constant gain, which is always zero. An easy way to visualize these two operations is to plot the location of poles and zeros of this transfer function and plot where the excitation frequency is. In this generic example here, we have one pole and one zero, and the excitation frequency is there, s equals to j omega. The phase of the transfer function can be calculated by looking at the angle that these lines that connect the point of excitation to the poles and zeros is. The first step towards calculating the phase of the transfer function is to define these individual angles here, that in this specific case will correspond to these two terms. Let's call this angle θ1 and this angle θ2. They can be easily calculated using simple trigonometric functions because omega is known, the location of the pole and the zero is also known. Once θ1 and θ2 are found, then the phase of the transfer function is simply the phase of all zeros, in this case θ1, minus the phase of all poles, which in this case is θ2. This same representation can help to calculate the magnitude of the transfer function. If this distance here from the pole to the excitation frequency is a, and this distance is b, this means that the magnitude of the transfer function is simply the magnitude of all zeros, b, divided by the magnitude of all poles, a. Should this function have another pole, say here, and the distance to that pole to the excitation frequency is c, then this would become b over c times a. This is the first step towards developing Bode plots and using stability analysis in the frequency domain. The objective of the Bode plot is to now represent this phase and magnitude of the transfer function for a wide range of frequencies. But stability was analyzed in one of our early lectures, so why introduce another way to evaluate stability and characterize a system? Well, the biggest advantage of frequency domain is that everything can be done experimentally. Bode plots can be obtained experimentally by subjecting a system to a sinusoidal waveform. The true representation of the frequency response of a system is the Bode plot. To build a Bode plot, we introduced several elementary building blocks, and because the Bode plot is expressed in a log scale, then it is sufficient to draw the Bode plot for each individual building block and then add them up. These building blocks are listed here. The first one is a constant gain. A constant gain is a real number, meaning that it will lie on the real axis. But for example, if the magnitude of that gain is k, we can see that this distance is k and the angle of that arrow is 0. If the value is negative k, the distance to the origin is still k, but now the angle is negative 180 degrees. So for a constant gain on the Bode plot, we'll see a constant line for the gain, which is k or 20 log of k if you're dealing with decibels, and the phase will either be 0 or negative 180 degrees. The next building block is the pole at the origin. When you deal with the pole at the origin, the function will look like 1 over s, which is the same as 1 over j omega. If you multiply the top and the bottom of that equation by omega, we end up with negative j times 1 over omega. If the function is now represented on the s-plane, the function will lie on the negative imaginary axis, and the magnitude will be negative 1 over omega. We can see that this magnitude of negative 1 over omega decreases as the frequency increases. And you can see on the other hand that the phase of this transfer function is always negative 90 degrees. The magnitude of the transfer function can be written as 20 log of 1 over omega, which is the same as negative 20 log of omega. This gives rise to a slope of negative 20 decibels per decade. So for each frequency decade, the magnitude on the Bode plot goes down by negative 20 decibels. The next element of our system is the zero at the origin. A zero at the origin would be characterized as g of s equals to s, or g of j omega equals to j omega. The representation of this function in the s-plane is very similar, but now the function lies on the positive real axis, and the magnitude here is simply omega. We can see that the phase of this transfer function is always 90 degrees for all frequencies, but the magnitude of this transfer function increases as omega increases. The magnitude in decibels is 20 log of omega. So for each frequency decade, the Bode plot goes up by 20 decibels. We can clearly see the similarities between the pole at the origin and the zero at the origin. The only difference is a negative sign. Whereas the magnitude goes up for the zero, it goes down for the pole. The phase of the pole is negative 90 degrees, the phase of the zero is plus 90 degrees. The third building block is the real pole. And for the real pole, the transfer function will become 1 over s divided by omega 0 plus 1. This is the standard form needed for Bode plot analysis, so all gains are removed from the transfer function. They can be treated separately as a constant gain. Omega 0 here is what we call the cutoff frequency of that specific pole. For the real pole, the analysis described in lecture 16 revealed 3 different cases. The first case is when the frequency of excitation is lower than the cutoff frequency. We are here at omega 0. The magnitude of the Bode plot for frequencies that are lower than omega 0 is 0. Past omega 0, we know now that the magnitude of the Bode plot starts to decay by negative 20 decibels per decade. At omega 0, the magnitude of the transfer function is 20 log of 1 over j omega 0 divided by omega 0 plus 1. This is 20 log of 1 divided by 1 plus j, which is the same as 20 log of 1 divided by square root of real part squared plus imaginary part squared. This is 20 log of 1 over square root of 2, which is the same as negative 20 log of square root of 2, and this is negative 3 dB. So exactly at the cutoff frequency, the Bode plot goes down by negative 3 dB. The phase of the transfer function is also affected by the real pole. The phase up to the cutoff frequency is 0, and the phase past the cutoff frequency is negative 90 degrees. The phase passes at negative 45 degrees at the cutoff frequency. The next element is the real zero, and you can see again here that the real zero is similar to the real pole, with the exception of a sign for both phase and magnitude. For the same cutoff frequency of omega 0, the Bode plot up to the cutoff frequency has a magnitude of 0 decibels, and past the cutoff frequency, the magnitude now increases by a factor of 20 decibels per decade. Exactly at the cutoff frequency, the magnitude goes up by 3 decibels. The phase follows a similar trend. Up to the cutoff frequency, the phase is 0, and past the cutoff frequency, now the phase tends to positive 90 degrees, passing at positive 45 degrees at the cutoff frequency. The final and the most complex building block is the imaginary zero or poles. Imaginary zero or poles need to be written in the standard form as follows, where omega 0 is the cutoff frequency again, and zeta is the damping ratio. Zeta, of course, will be comprised between 0 and 1 for stable systems. The imaginary pole or imaginary zero will act similarly to having 2 zeros or 2 poles placed at the exact same cutoff frequency. There is one exception to this rule. That is what occurs exactly at the cutoff frequency. So let's analyze the imaginary zero. Up to the cutoff frequency, the imaginary zero will have a magnitude of 0. And past the cutoff frequency, because this is equivalent to 2 zeros, the magnitude now goes up by positive 40 dB per decade as opposed to 20 for 1. The phase of the transfer function goes from 0 to 2 times 90 degrees, 180 degrees. And at the cutoff frequency specifically, the magnitude of the transfer function is 20 log of 2 zeta. This means that if zeta is greater than 0.5, then the magnitude of the cutoff frequency would see a bump that goes up. If zeta is less than 0.5, then this bump goes down at the cutoff frequency. Now let's take a look at the imaginary pole. The imaginary pole also acts like having two poles at the same cutoff frequency, with the exception of what happens at the cutoff frequency itself. Up to the cutoff frequency, the magnitude is 0 decibels, and past the cutoff frequency, the magnitude decreases by 40 decibels per decade, or the equivalent of two poles placed at that cutoff frequency. The phase goes from 0 to negative 180 degrees. What happens at the cutoff frequency? The magnitude here is negative 20 log of 2 zeta, where zeta is the damping ratio. If zeta is greater than 0.5, then you would see the body plot going down at the cutoff frequency. And when zeta is smaller than 0.5, the body plot goes up as shown. For further details, please refer to lecture 17 and lectures 22. Another important aspect of any system in frequency domain is its stability. And the Nyquist stability criterion is one way to infer stability of a closed-loop system. The advantage compared to temporal domain techniques is that here we can determine the body plot based on experimental data, and based on the body plot infer the stability of that system if used in a unit feedback loop. We all know how to define stability of a system. We are looking at the transfer function, and you expect all poles of that transfer function to lie in the stable zone, that is, the left side of the S-plane. Let's assume that our transfer function is T of S, which is composed of a controller function C of S and a plant function G of S. The system is said to be open-loop stable if all poles of T of S are located on the left side of the S-plane. If you close the loop, then the transfer function becomes C times G divided by 1 plus C times G. This system, this closed-loop system, is said to be stable provided that all poles of T of S are on the left side of the S-plane, or provided that 1 plus C times G has roots that lie on the left side of the S-plane. These are the zeros of the characteristic equation 1 plus C times G. So the closed-loop stability can be stated in two ways, and they are equivalent. The poles of T of S lie on the left side of the S-plane, or the zeros of the characteristic equation of T of S lie on the left side of the S-plane. These two statements are the same. For example, if our function is simply S plus A divided by S plus B, we can say that the open-loop system is stable if C times G has negative real poles, that is, B must be greater than 0. For closed-loop stability, the zeros of 1 plus C times G must have negative real parts. In this case, you are left with 1 plus S plus A over S plus B, and this is S plus B plus S plus A. If the roots of this characteristic equation have negative real parts, then the system is said to be closed-loop stable. Something worth noticing is that the poles of the characteristic equation are the same as the poles of the open-loop transfer function, as we can see here. Using the Cauchy's argument principle, we can define a way to assess the stability of this system. Remember that we are looking for unstable zeros of the characteristic equation. Cauchy's argument principle states that if you take any point P on the S-plane and trace these lines from every pole and zero to that point P, the equivalent representation of that point on the W-plane, or the magnitude and the phase of the transfer function when the excitation is P, can be represented as a vector as follows. Phi is the angle of the transfer function, or the phase of the transfer function, which in this case is the angle of all zeros, phi 2 plus phi 1, minus the sum of the angles of all poles. The magnitude of this vector, or the distance to the origin, is the same as we covered before for phase and magnitude. Let this distance be d1, this distance be d2, this distance here d3, and d4. A will be the magnitude of all zeros multiplied together, that is d1 and d2, divided by the magnitude of all poles divided together, d3 and d4. If each point on the S-plane has an equivalent representation in the W-plane, then a contour composed of several points will make a contour composed of several points on the W-plane as well. Something interesting happens here. Depending on how the contour is defined on the S-plane, the equivalent contour on the W-plane may or may not encircle the origin. This can be easily seen. Let's, for example, define contour gamma 2. and take this point of interest P and make this point P do a full revolution around the contour gamma 2. We can see that as this point revolves around the contour, the phase of each pole and each zero will simply oscillate back and forth and will never do a full rotation of 360 degrees. This means that on the W plane, we shall see a contour that displays the same behavior, perhaps something like this, where the angle phi increases and decreases, but it comes back to its initial value without doing a full revolution. However, if the contour is defined around a pole or a zero, things will change. As you can see in this example, if you look at a contour gamma 1 which encircles a zero, as this point of interest is moved around the contour, we see that the angle of the zero inside that contour will do a full revolution of 360 degrees. This means that on the W plane, a similar behavior must be observed. The contour on the W plane encircles the origin once, and it does so that a phi now can do a full 360 degrees before it comes back to where it started. The contour on the S plane is typically defined in the clockwise direction. This means that we can now watch the encirclements of the origin in the W plane and infer whether or not there is a zero inside of that contour. If there is a zero within the contour, then the contour on the W plane will encircle the origin once in the clockwise direction. If there is a pole inside of that contour, then the encirclement will be in the counterclockwise direction. If there is both a pole and a zero inside of that contour, then no encirclement of the origin will be observed on the W plane because the pole and zero cancel out. We can thus state that a contour map of a complex function will encircle the origin n times, where n equals to z minus p. Z is the number of zeros and P is the number of poles of the function inside the contour. Now, how do we apply this to assess the stability of a closed loop system? Well, we can simply define this contour in a way that it encompasses the entire unstable region, and the unstable region is simply the entire right side of the S-plane. If there is any poles or zero inside of the unstable region, we'll see encirclements of the origin. Remember that the number of encirclements will be Z minus P, where Z is the number of unstable zeros of the characteristic equation, and P is the number of unstable poles of the characteristic equation. Now remember that early comment, the poles of the characteristic equation are the same as the poles of the open loop transfer function, and thus P is always known. Z, the zeros, will change from the open to the closed loop system. However, Z will change between them. We can assess the number of unstable zeros as n plus P, the number of encirclements of the origin in the clockwise direction, plus the number of unstable poles of the open loop transfer function. This is not very practical because you now have to deal with the characteristic equation of the system, that is 1 plus the line function times the controller. If you subtract 1 from Cg plus 1, we are left with C times G, and this is the open loop transfer function. The Nyquist plot or the Nyquist contour now, instead of encircling 0, will encircle -1, and thus the Nyquist stability criterion can be stated as follows. An open loop transfer function L of S is closed loop stable if and only if the number of counterclockwise encirclements of the -1 point is equal to the number of poles of L of S with positive real parts. Why counterclockwise? Because counterclockwise encirclements are negative. For each unstable open loop pole, one encirclement in the counterclockwise direction must be observed to ensure stability of the closed loop system. To carry out this analysis, we need to come up with the Nyquist plot. But remember that the Nyquist plot is simply the Bode plot without the frequency information. Both phase and magnitude are displayed on the Bode plot, and are also displayed on the Nyquist plot. But between them, the frequency information is removed. To draw the Nyquist plot, we need to evaluate 4 points. The first one is the contour at infinity, and it turns out that the contour at infinity maps to a single point. The second point is where the frequency tends to 0, the third point the frequency tends to infinity, and the fourth point is where the plot crosses the real and imaginary axis. Now that we have a way to assess the stability of a closed loop system based on its open loop frequency response, we can put a number on how stable a system is. This is the job of gain and phase margins. They quantify how close the system is to instability. The objective here is very simple. Consider a closed loop transfer function in the form of L of S divided by 1 plus L of S. If the denominator of this transfer function becomes 0, then the entire function goes to infinity. This function becomes 0 if L of S equals to -1, or the magnitude of L of S is equal to 1 and the phase of L of S is -180 degrees. This will make the denominator 0 and the magnitude of the transfer function tending to infinity. Thus, for the system to be stable, this combination of a magnitude of 1 and a phase of negative 180 degrees must be avoided at all costs. On the Nyquist plot, this combination is very clear and is very easy to see. This is nothing else than the negative 1 on the Nyquist plot. The stability margin is basically a measure of how far the function is from that specific point. In this case, this distance would be the gain margin, this angle would be the phase margin. Where is that on the Bode plot? On the Bode plot, the only difference is that instead of looking at a magnitude of 1, we are looking at a magnitude of 20 log of 1, which is 0 decibels. Thus, on the Bode plot, the combination that must be avoided is 0 decibels and the negative 180 degrees of phase. The phase margin is easier to see from the Bode plot. We're going to start at the point where the magnitude of the transfer function is 0 decibels, determine the frequency that leads to 0 decibels, and then look at the current phase of the transfer function. The distance of the current phase to negative 180 degrees is the phase margin. To calculate the gain margin, we go from a point where the system reaches negative 180 degrees and we check how far the gain is from 0 decibels. In this specific case, the phase margin, in this specific case, the gain margin is infinity because the transfer function theoretically never touches negative 180 degrees. And this is a good example to visualize how important it is to define gain and phase margins. The gain margin appears to be infinity, but if you look closer at this transfer function, the function, even though it is closed loop stable, it is very close to the critical point that may lead to instability. If a gain margin is positive, that means that that amount of decibels can be added to the closed loop transfer function before the system becomes marginally stable. The system as it stands then is closed loop stable. If the gain margin is negative, this means that that amount of gain margin must be subtracted from the Bode plot for the system to become marginally stable. As it stands, the system is then unstable. Adding or subtracting decibels from a transfer function is equivalent to multiplying the gain of the transfer function by a value that is higher than 1 when you add decibels or smaller than 1 when you subtract decibels from the transfer function. The same can be said for the phase margin. If the phase margin is positive, then the system can be subjected to an additional delay before it becomes marginally stable. The system then is closed loop stable. If the phase margin is negative, it means that as it stands, the system is closed loop unstable, and that amount of phase margin must be subtracted from the phase to make the system marginally stable and eventually stable. Let's consider this example here where the solid blue line on the left is the original magnitude of the transfer function. We see that the cutoff frequency occurs early here and the phase margin is given there. If the transfer function is multiplied by a number that is greater than 1, then the Bode plot will shift up, and if the transfer function is multiplied by something that is smaller than 1, then it will shift downwards. We see that in this case, as the Bode plots shift upwards, the cutoff frequency tends to the right. And for this specific combination, the system that was stable now becomes closed loop unstable, because at the cutoff frequency, the phase is negative 180 degrees. This will occur every time the gain is changed in the transfer function, for example, by adjusting a controller gain. A delay in the transfer function will change the phase of the transfer function. Back to our example, at this specific cutoff frequency, we have this much phase margin. But if an additional delay is added to the system, say a communication delay in a microcontroller or in a network, and if it increases by this amount, then the system becomes closed loop unstable. Calculating the phase and gain margins of a system is very important and crucial to design a controller based on the frequency response. To find the phase margin, here are the 3 steps to follow. Step 1, find the crossover frequency. At the crossover frequency, the magnitude of the transfer function is 1 or 0 decibels. Step 2, find the phase of the transfer function at the cutoff frequency. The phase margin can be calculated in step 3 as 180 minus the magnitude of the phase at the cutoff frequency. For the gain margin, first find the frequency where the phase of the transfer function is negative 180 degrees. Remember that you find that number by setting the imaginary part of the transfer function to 0. Then find the gain of the transfer function at that specific frequency. In step 3, then, we can calculate the gain margin in decibels as negative 20 log of the magnitude at that specific phase. The last topic we covered is the state space model, or state space representation. The basis of a state space model and analysis is to replace Laplace transform with linear algebra, and this is the introduction to a new type of control systems that is covered in a different course. However, we are indeed required to cover a state space model in this course. The state space is a set of variables that provides the future states of the output of the system for a given input. The state variables are typically defined as elements in the system that are capable of storing energy in some form. For example, in a mass spring damper system, good candidates for the state variables are the kinetic energy and potential energy stored in a spring. In an electrical system, the energy is stored in an inductor or capacitors are also good candidates for the state variable. There are many ways to define state variables for a given system, and they all provide a valid set of state variables. Our objective is to create simple first-order differential equations, as opposed to higher-order differential equations as we have been using up to this point. If you're dealing with a system of order n, then we'll end up with n first-order differential equations. The state space representation is given by these two simple functions. X dot equals to a times x plus b times u, where x is a vector that contains the state variables, x dot is the derivative of x, a and b are matrices to be found based on the model, and u is the input to the system. This equation links the derivative of the states with the states themselves and the input. The second equation in the state space representation is y of t equals to cx plus d times u. C and d are matrices to be determined, and y is the output of the system. So this equation links the output to the current states and the input. More on linear state space control systems will be offered in an elective course in the 4th year. And these are all the topics covered between lectures 16 and 23. In this lecture, we'll find a set of practice exercises. The solutions are not provided, but the final answer is given. There are 150 exercises with full solutions explained in videos, which is plenty of materials to teach you how to solve this problem. Now it's time to sit down and try these ones on your own. And remember that you can always check the solution using MATLAB. For more practice exercises, please refer to lecture 15, where the first part of the course is covered. This brings our course to an end. I would like to thank all of you for bearing with me through 23 lectures, 200 exercises, and 140 videos. I do hope that you enjoyed control systems, and I hope to see you again in a future class. In the meantime, if you are interested in part or full-time research opportunities in mechatronics and robotics with applications to biomedical engineering, please check out my research lab website, biomechatronics.ca, for more details on research opportunities and current research projects. Thank you very much. See you again next time.